Hello everyone, my name is Willemijn Ouwern and I'm an application scientist at Qubits, and today I would like to share with you an overview of the current and future requirements on quantum control stacks for spin qubits. Just a quantum chip on its own, without any external input, is just a dead piece of material. To exploit the power hidden in these quantum systems, we need to add electronic control. We can divide the electronic control into two categories: the DC power supplies and the microwave generators. Let's first focus on the DC supplies. These sources are designed to provide an ultra-stable voltage and current output and are used to set certain conditions that are kept constant during the experiment. For spin qubits in germanium, we can think of the voltage barriers that are applied to deplete certain regions from charge carriers. In this way, a quantum well, or quantum dot so to say, can be engineered to capture single spin-fold charged particles. In this case, the voltage barriers are tuned to capture holes. Changing the polarization would allow for the manipulation of electrons. Device-specific voltage requirements depend heavily on the material platform, material thicknesses, and gate configuration, as this will determine the physical size of the quantum dot, its energy level spacings, and the electrical coupling of the gates to the dot. The two-level system for the qubit can be generated by applying a constant magnetic field to split the degenerate spin states. Typically, this is tuned to be on the order of several to tens of gigahertz. By varying the tunnel barrier, a hole can be loaded. When the system is tuned such that the spin down level is below the energy of the lead, while the spin up level is above it, the system can be initialized in the spin down state. Manipulation of the spin state can now be accomplished through adding energy to the system at the according frequency, defined by the Siemens splitting, within the decoherence time of the qubit, bringing us to the need for pulsed high-frequency signals. The RF frequency requires to be addressable within the line width of the qubit, and an entire pulse sequence should take well within the coherence time of the qubit. Besides manipulating the spin state, fast electronic responses are also needed when changing or pulsing gate voltages during the experiment. An example of such an experiment is spin shuttling. Here the RF source is connected via bias T to the gate. The DC supply provides the offset, while the RF source provides the fast manipulation. The bias T connection disconnects the DC and RF paths due to the inductor and the capacitor. Lastly, RF signals are commonly used for readout purposes. Here we give an example of charge sensing through a sensing dot that is being read out by an on-chip resonator. Let's say you would like to read out the spin state of the hole in the left quantum dot. Putting a sensing dot close to the quantum dot creates a capacitive coupling between the two. Now, the presence of a charge carrier in the left dot will influence the eigenfrequency of the sensing dot. Another capacitive coupling to the readout resonator makes it possible to read out the shift in eigenfrequency of the resonator. When we tune the energy of the lead to be in between the spin states, the spin up state can leave the dot, while the spin down state will be trapped. Through the capacitive couplings, we read out different eigenfrequencies of the sensing dot resonator system. A lot of requirements on the electronics have already been discussed by discussing various experiments. However, a very important aspect that we have not taken into account is the analog performance. When we need DC voltages, how DC do they need to be? To understand the importance, we can visualize the effect of several disturbances on our system. For example, noise on a barrier gate in between dots will affect the tunnel coupling between the dots, but will also affect the relative depth of the quantum wells and with that alter the energy levels of the respective dots. In DC power supplies, there are two main sources of noise. Firstly, noise on top of the offset that is inherent to the power supply, and secondly, the drift of the offset over time, which is usually due to temperature. The inherent noise level has an immediate effect on the experiment, while the offset drift varies over a larger timescale. However, this will require periodic recalibration of your system. The amount of disturbance that is tolerated depends on the sensitivity of your system to such changes. Since changes in the gate voltages affect the level spacings, this will result in your RF pulses not being correctly calibrated anymore. It may happen that your pi pulse doesn't yield in a full spin flip, or even overshoots. Now let us assume perfectly stable DC power supplies and no disturbances from the sample's environment. If we solely look at the parameters of the RF supply, any noise in frequency, amplitude, and pulse length will affect the energy absorbed by the system, and therefore will alter the calibration of a pi pulse. The last parameter that is important to RF supplies is the phase. If we want to extract information from the phase, we need to compare the phase that comes back from our system to the phase of our instrument. If there is drift in the phase of the instrument, this comparison is no longer possible and we cannot extract any information. Besides that, synchronization is also very important to make this comparison, and also comes into play when performing multi-qubit gate operations, where the timing of individual qubit operations and interactions need to be well organized in time. Lastly, it is important to be aware of the dispersion due to cables. The envelope shaping consists of a spectrum of frequency that yields in the envelope as a time response. However, the velocity depends on the frequency, deforming the envelope that reaches your qubit system. This can be countered by deforming your pulse shapes such that the dispersed version at your sample yields the desired shape. By now we understand what type of pulses we need and the requirements for it. Let's see how this looks like in a hardware setup for about 20 qubits. Here you have an example of the arsenal of equipment that one should think about. This conventional method is costly, takes a lot of energy to set up and maintain, and with that is not suitable for scaling up. In the recent, let's say 5 years, the field of quantum control stacks have undergone a major shift. Qubit dedicated hardware has been developed. Fully integrated architectures offer you all you need for qubit control and readout in a massively scalable fashion, and with modular components to personalize your electronic stack to your experimental needs. Where the arbitrary waveform generator used to be a staple instrument, it is now being replaced by onboard sequence processors that allow for generating waveforms on the fly. Waveform envelopes can be stored in the onboard memory and modulated in real time, giving you the flexibility to vary amplitude, offset, phase, and frequency on the fly without the need to open a connection to the PC to reload your waveform. Such sequencers also allow for onboard data processing, where only the data needs to be stored, freeing up internal memory on the fly and decreasing the amount of time needed after the experiment to transfer the data to the PC. Onboard processing also allows for fast feedback, as decision trees can be performed within the instrument, bypassing the need to establish communication to the PC and back. A great example of the experimental speedup that can be accomplished using such fully integrated systems is shown by measuring a chevron plot. This is a typical experiment mostly for characterization purposes, where two parameters are swept: the amplitude and the length of a pulse. Switching from software-controlled loops to pulse parameterization removes significant overhead. On top, active reset, due to fast feedback, allows further reduction of the experimental time. In the end, an experiment that takes more than an hour boils down to merely seconds. Even though the development of quantum control electronics have undergone a major transformation in the past years, the field is still very much in development. It specifically is focusing on upscaling, we see a strong focus on the increasement of channel density and increasing this beyond the current generations. With upscaling the channel density, the cost per qubit should go down. Fast feedback protocols should be also extended over these larger systems to fulfill the requirements for full-fledged quantum computers, where active resets, qubit state-dependent gates, and real-time decoders for quantum error corrections are all part of the standard protocols. Lastly, I would like to emphasize quickly the trend in software that accompanies the electronic hardware. With systems becoming more complex, higher-level software languages become necessary to quickly initialize and characterize the system. To summarize, the new generation of quantum control electronics are dedicated and integrated, yielding in experimental speedup a scalable and modular system with inherent synchronization and fast feedback.